So you're just walking around minding your own business one day when suddenly there was a bright light. The bright light shone down the sky, and before you know it, you started to float up into the air. And at that moment, you realized that you were being abducted. And it was so frightening that you just fell unconscious. By the time you regained your consciousness, you find yourself locked in some sort of room. You decide to look out the window and you see the Earth. And so you thought, I must be in space right now. And so you decide to walk across the room and look through the other hole. And through that hole, you saw a robot walking past you. And then you saw another. And then another one. And at that moment, everything added up. You were actually being abducted by robots. And now you're locked up in a room in a spaceship filled with robots. And the robots abducted you probably because you work for the secret agents. And you wanted to scream and shout and ask for help. However, you figured out if you do scream and ask for help, it might make the robots a bit mad, and you don't really want to make the robots mad. So you stayed calm, and you checked down your pockets to see if there's anything there that might help you. Oh, and look! There's your phone. They decided to take your phone out and text your friend Frank. Hey look, just don't ask questions about how there is cell signal up in space, alright? So that's a fair enough request. You need to tell Frank the number of robots that's on that spaceship so that he can send the right number of men to come up and help you from that spaceship. So you looked back out through that little hole and started counting the robots. But then you realize that method is never going to work. It's going to take ages to count all the robots, and even then, how do you know if you counted all the robots? There's no way you can find the exact number of robots on that spaceship being locked in that room. So the best you could do is to just estimate. So he kept staring out that little hole, hoping there might be some little hints about the robots that could help you estimate the population of the robots on that ship. And then you realize something about these robots. Now, while all the robots have got the exact same build, there is one tiny detail which can tell apart each robot from each other. You see, when these robots are being manufactured and assembled, they all have a little number printed on their polished metallic bottom. These numbers are pretty much the robot's ID number and the order in which the robot were assembled. The first robot assembled would have an ID of 1. Then the second one would have had an ID of 2, then 3, then so on. So you thought, maybe that can help you one way or another. So you looked out that little hole for a while, staring at robots' bottoms, trying to get ID numbers of random robots that walked past. And over the next 15 minutes, you saw 5 robots randomly walking past you. And you made a mental note of the ID numbers that were printed on their bottom. So you got 5 ID numbers of 13, 55, 72, 97, and 130. And, you know, that's something, isn't it? You can get a bit more information using these ID numbers. You know now that there must be at least 130 robots on that spaceship, because that's the biggest ID number that you've seen. But even then, there might still be millions of robots on that spaceship. You don't know. But using those 5 ID numbers that you've collected, what's a good way to estimate the number of robots that's on that spaceship? How would you even estimate the number of robots on that spaceship using the ID numbers that you've got? So you thought, you scratched your beard, you scratch your ears, you do whatever people do when they want to think. And then you had a light bulb moment. You've got a method. So for the purpose of explanation, let's say there are N robots on this spaceship. Now, of course, we don't know what N is. That's the number that we're trying to estimate. Now, imagine all the robots on that spaceship in one long line, in order of their ID. So you have the robot with the ID of 1 at the beginning of the line, followed with the robot with the ID of 2, then 3, then 4, then all the way to the robot with the ID of N. The ID of the robot at the end of the line will just equal to the number of robots that was in that line. And currently we have the ID of 5 of the robots in that line. We'll say that these 5 IDs are our samples that we've collected. So we can take the numbers of these samples and mark where they would be on this line. So the 13th robot will be here. Here's the 55th one, here's the 72nd one, the 97th one's here, and here's the 130th one. As you can see, our 5 samples, when marked along that line, are all pretty much spaced out from each other. So now let's go to the beginning of the line. Say you started from the beginning of the line and you started walking. How many robots will we need to walk past until we get to the 13th robot, or the first robot that was in your sample? Well, you can count. You need to walk past robot 1, robot 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and robot 12. And then you get to robot 13. So you need to walk past 12 robots before you get to the 13th robot. Or another way you can think about this is, say if you start from robot 0, which is the beginning and it doesn't really exist, how many robots will you walk past until you get to the 13th robot? You can just simply do 13 minus 0 and then minus an extra 1. So now you're at the 13th robot, and if you keep walking, how many more robots will you need to pass until you get to the next robot in your sample, or robot number 55. Or again, you could count, you could go 14, 15, 16, 17, all the way up to 54, which is the robot that you'll meet right before getting to robot number 55. And if you actually go through it and count, you'll find that the answer comes out to 41 robots. But a simpler way to get this number 41 is to just take 55 and subtract it by the 13. And then subtracted by an extra 1. So similar to what we did the first time round, the finish position minus the starting position, and then minus an extra 1. The reason we need to subtract the extra 1 is because if you take 55 and subtract it by the 13, this will be the number of robots between the 13th and the 55th robot, including the 55th robot itself. So you need to take out that extra 1 so you don't count the 55th robot. And then you can do the similar bit of maths for the rest of the line. If you're at the 55th robot, you have to walk past 16 robots to get to the next sample, the 72nd robot. If you're at the 72nd robot, you need to walk past 24 robots to get to the 97th robot. And if you're at the 97th robot, you need to walk past 32 more to get to the 130th robot, which is the robot with the biggest ID in our sample. So there we find the size of the spaces, number of robots between each of our sample along that line. However, there is still one more space, one more bit left. If you're at the 130th robot, how many robots we need to walk past until you get to the end of the line? Well, maybe there is just one more robot until the end of the line. You need to walk past one more robot from 130th one to get to the end of the line. Well, maybe there's still thousands of robots left that you need to walk past from the 130th one until you get to the end of the line. However, the IDs of the robots that you've written down are quite random. You didn't choose which robots walked past your sight of vision, so you can say that your sample that you've collected is quite random. The chance of any of these robots walking past you are probably pretty much the same, and it just happens that these 5 robots are the robots that walked past you at the moment you were collecting the data. And if the samples we've collected, the ID of the robots, are really random, then most likely these robots will be distributed evenly along that line. You should have to walk past about the same number of robots each time to get from one sample to the other. Or basically these spaces should all be about the same value. So it's probably less sensible to say that this last space will only have 1 robot or 1,000 robots. So what would be the most reasonable guess for the number of robots between the 130th robot to the end of the line? Well, that last space there, the number of robots from the 130th robot to the end of the line, will most likely be the average of all of the previous spaces that we've calculated. So let's do that. Let's try to find the average of the size of these spaces, of these gaps. Well, you can add up all these numbers and you get 125, and because there's 5 numbers, we can divide it by 5, and we get the average of 25. And so in our estimate, we predict that if we're at the 130th robot, we need to walk past 25 more robots to get to the end of the line. And that will mean the last robot will have an ID of 155, which is 130 plus 25. And so we conclude that there's probably about 155 robots on that spaceship. Of course, this is an estimate. We might be way off. Who knows? In fact, what if we make an equation out of this entire process? To get the number of robots that was on that spaceship, to get that number 155, we basically just added the biggest ID that we found with the average of all the spaces between the samples that we've collected. So let's put that in some sort of an equation. Let's say there are N robots on that spaceship, and we've collected some number of samples which I'll call K, and let's say the biggest ID that we've collected in our sample is M. So basically N, the number of robots on that spaceship, will be the biggest ID number plus the average of all the spaces. Well, the biggest ID number, as we said earlier, will be M, and the average size of the spaces will equal to the sum of all the spaces divided by how many spaces there are. The sum of all the spaces work out to equal to M minus K. You can pause the video at this point to see why, and we have to divide that by the number of spaces, which equals the number of samples that we've collected, or K. So there we have a neat little equation to help us estimate the number of robots on that spaceship. We have the equation N, the number of robots on that spaceship that we predict, equals to M plus M minus K divided by K, where K is the number of samples we've collected and M is the biggest ID number that we've collected. But hold on, why am I going off topic? You need to text your friend Frank to tell how many robots are on that spaceship so he can send some men to help you. Well, shit. But that's alright, if you're stuck on that spaceship, at least you now know how to calculate the maximum in a discrete uniform distribution, given a sample of a certain size. In statistics, the problem of trying to estimate the size of a population in a situation like this is more commonly known as the German tank problem. Quoting from Wikipedia, the German tank problem involves estimating the maximum of a discrete uniform distribution from sampling without replacement. In a discrete uniform distribution, the probability of any of the outcome happening is the same. If you have 10 balls and you were to write a number on each of the balls and toss it into a bag, the probability of taking any of those balls out will be the same. In our example, the chance of any of the robots in that line walking past us is the same. The chance of you seeing robot number 2 walking past is the same as the chance of you seeing the robot number 69 walking past you. As the name suggests, this problem was originally used to estimate the number of German tanks. You see, during World War II, the Allies were curious about how many tanks the Germans were making. So what the Allies did was they looked for disabled German tanks, or they captured some of the German tanks, and then they looked for serial numbers on different components on that tank. For example, the gearbox of the tank had serial numbers on them, so they just collected those serial numbers and used that as their sample. And with that sample, with those collected IDs and the method that we've discussed earlier, they were able to estimate the number of tanks that the Germans were making. And so while the intelligence units were saying that the Germans were making thousands of tanks a month, the statisticians said otherwise. They thought the number was much lower. And guess who was closer? And of course, this problem isn't just limited with the number of tanks being made or the number of robots on a spaceship. Back in 2008, a man from London asked for serial numbers of people's iPhones. And using those serial numbers he collected, he was able to estimate the number of iPhones that was sold by Apple. But of course, there are more than one ways to skin a cat, and this method I've talked about is just one way you can solve the German tank problem. The solution I've discussed is more of the frequentist approach, but of course there's also the Bayesian approach to this very problem. But anyways, that's all I have time for. Thank you very much for watching this video, and I'll see you again whenever. Goodbye.